Hello everybody. We are going to present deep learning for nonlinear dynamics. I'm Xian Park.
Hi guys, I'm Shantanu.
Hey, I'm João Cortes.
Hi, I'm Sophie. Nonlinear systems are governed by chaos, which is an aperiodic long-term behavior and deterministic system that exhibits sensitive dependence on initial conditions. This means that these systems are theoretically deterministic, yet may evolve to exponentially different end states based on small changes in their initial conditions. Examples of these systems include financial markets and weather patterns, and in our case, fluid flow and neural circuits and dynamics. So the problem is, how can we better describe and predict these ubiquitous and important systems despite their nonlinearity? Our vision is to use deep learning to estimate Koopman embeddings of a variety of nonlinear systems to make time series predictions. The world is nonlinear, but our mathematical methods deal best with linearity, so we aim to represent the dynamics of nonlinear systems by mapping them to a linear space using Koopman embeddings.
Bethany Lush applied Koopman's embeddings through a deep learning approach named Deep Koopman. When proposing such a model, the authors only chose to analyze systems with well-known governing equations such as pendulum and fluid data passing through a cylinder. What if we could predict different nonlinear dynamics, resorting to Deep Koopman's way of thinking? To address this question, we used EEG data. What is EEG data? EEG data is a recording of the brain's electrical activity collected non-invasively by placing electrodes on the scalp. It includes synchronous information of different areas of the brain simultaneously. For our group project, we chose CHBM MIT dataset for 2022 pediatric subjects. The dataset included 23 electrodes per subject recording for an hour. To achieve this goal, we organized our work in 4 steps. EEG data preprocessing. In this step, we adapt filtering behavior and recording artifacts. Autoencoder, where we develop a more efficient PyTorch based on existing literature. EEG net encoder, where we adapt CNN-based approaches towards more effective time series. And experimentations, ablations, where we can further enhance the architecture and other fine-tunes.
The core challenge we faced was designing a system that was capable of handling 2 vastly different nonlinear data, fluid dynamics and brain waves. To solve this, we did not just build 2 separate models. Instead, we utilized a pre-trained BERT-based uncased model as our shared backbone. And since fine-tuning a transformer is a very massive task, so we used low-rank adaptations over the BERT-based model to create a more performance-efficient fine-tuned model. We use specific adapters for EEG and CFD data to project the input data into the space which transformers can understand. The data is processed using the EEG adapters and the CFD adapters. And while decoding the data, we again use 2 very different decoders. One is for the EEG and the CFD, which are able to get the spatial dimensions back to the original data set, so that we are able to use the mean squared error loss to finally train our model overall. If you see the model layer architecture in depth, you see that the CFD data has spatial dimensions of 50,3, whereas EEG has 23 channels. So we use these 2 input heads to get the dimensions into 768, which is the vector dimension of the BERT-based model. And then again, the 2 decoders help us get the dimensions back to the original data set, as we talked about before. Now I'll move on to the main workflow that we employed. So as we told before, that we decided not to train our model 2 times because to take care of the different dimensions of the dataset, we used a domain logic which was able to split the adapters real time whenever a new dataset came on the basis of whether it was a CFD data or an EEG data, and then send the data into the BERT-based encoder, which used LoRa techniques to fine tune it. And then again, there was the similar domain logic which helped us in splitting the data into either the CFD decoder or the EEG decoder, through which we were able to get the CFD and EEG time series and then compare it to the actual data present and overall fine-tune our model.
Okay, now I'm going to talk about our result. This is the learning curve. Our experiment showed that the unified deep Koopman style architecture can learn low-dimensional linear embedding that captures the dynamics of both fluid and EEG time series very well with low MSV loss. We trained the model on a 800 GPU, and it only takes about 4 hours. Next, this is the prediction part. The strength of our model is that you can easily change the input head depending on the task. Plus, thanks to the pre-trained BERT as a universal shared encoder, our model achieved more robust performance compared to the vanilla deep Koopman. In conclusion, our work shows that the single Koopman-based framework can meaningfully handle very different multi-dimensional nonlinear systems from fluid to the brain signals. Conducting more ablation studies is part of our near future work. This is the reference. Thank you for your attention.